We all think of physics as that really hard class in high school, right? Well, today we're going to flip that on its head. I want you to think of physics as something totally different, a detective's toolkit. Seriously, a set of powerful thinking tools for solving the mysteries of everything. So let's crack open that toolkit. I just love this quote. Physics is the language nature uses to write its stories. Isn't that beautiful? It gets right to the heart of it. Think about it. Every single thing happening around you, a leaf falling from a tree, a ball bouncing, the stars you see at night, they're all part of a larger story. And physics? That's the language. It's the grammar we need to actually read those stories and figure out what's really going on. Yup, that's right. For the next little while, you are the detective. And your case file? It's the entire universe. Ha, no big deal, right? But just like any great detective, you can't go in empty-handed. You need your tools to crack the case. So let's get you set up. All right, first things first. As a detective, you walk onto a crime scene and it's chaotic, right? The world is just like that. It's this huge, messy, complex place. It's a total whirlwind of information. So how do you find the important clues? You gotta cut through all that noise. And that's exactly what our first tool is all about. Cracking nature's secret code. Okay, tool number 1. We're calling it the composite sketch. You know exactly what this is. A detective talks to a witness, gets a description, and they draw a simplified sketch of a suspect's face. Well, physicists do the exact same thing with reality. They create a simplified version of a problem so they can actually study it. We call that a model. And here's a perfect example of that in action. So look on the left. That's a real car, right? It's got thousands of parts, different materials, complex electronics. It's a mess to try and analyze. But now, look at the physics model on the right. If all we want to know is how the car moves, do we really care about the color of the seats or the brand of the tires? Nope. So we just sketch it out as a simple box on wheels. All we care about is its mass and its motion. That right there is the magic of the composite sketch. So this is super important. A model isn't reality. It's a simplified picture of reality. And that's its superpower. It's all about intentionally ignoring stuff. You strip away all the complicated details that don't matter for the one question you're trying to answer. It lets you focus on the puzzle right in front of you. Okay, think about the best detectives in movies. They have this incredible gut feeling, right? They can walk into a room, take a quick look around, and just get a sense of what went down. They have a powerful hunch. Well, guess what? Physicists have a tool that's just like that. It's a way to make a really, really good guess. We're calling this one the back-of-the-envelope hunch. In physics, this is famously known as a Fermi problem. And the whole point here is not to get the perfectly exact down-to-the-last decimal point answer. No way. The goal is to get a good enough answer super fast just by using some common sense and making a few reasonable assumptions. It's all about getting in the right ballpark. So, let's try one out together. Here's the question. How many textbooks can you cram into a standard school backpack? I mean, yeah, you could go grab a backpack and a stack of books and physically count them. But where's the fun in that? We can use our new tool and figure it out, right here, right now. Okay, so how would a physicist tackle this? First, let's make a reasonable guess. How thick is an average textbook? Maybe 3 centimeters? Sounds about right. Okay, and a backpack? How deep is it? Let's say 30 centimeters deep. So the math is pretty simple, right? You just take the backpack's depth and divide it by the thickness of one book. And boom, there you go. The answer is around 10 books. Now, is it exactly 10? Probably not. Some books are thicker, some are thinner. But who cares? Without touching a single book, we know the answer isn't 2, and it's definitely not 100. We found the right ballpark figure. And in detective work, that is an incredibly powerful clue. All right, every detective has to know the law, right? There are fundamental rules you just can't break in an investigation. Well, the universe is the same way. It has its own set of rules, and a physicist's job is to know those rules inside and out. So, tool number 3 is the laws of the land. This is a two-parter. First, we'll look at something called dimensional analysis, which is really just the basic language of our measurements. And then we'll see how those rules behave when things get really, really big or really, really small. That's called scaling. Okay, let's start with the absolute basics. Believe it or not, pretty much everything we can measure in the universe, speed, force, energy, you name it, can be boiled down to just 3 fundamental things. Mass, which we'll call m, length, we'll call L, and time, we'll call T. That's it. These are like the 3 primary colors of reality. And here's the golden rule. This is so important. Any equation that actually works, any real law of physics, has to have the same dimensions on both sides of the equal sign. The stuff on the left has to match the stuff on the right. If it doesn't, the equation is just plain wrong. It's like a secret cheat code for checking your work. Okay, so how does this idea of dimensions lead to scaling? Let's check it out. I want you to picture a tiny little cube. Just for fun, let's say its length is 1, its surface area is 1, and its volume is 1. This is just our starting point, our little reference cube. Now watch this. This is where it gets really cool. What happens if we just double the length of that cube? Okay, its length goes from 1 to 2. Simple enough. But look, the surface area doesn't just double, it quadruples. It goes up by a factor of 4. And the volume, it goes up by a factor of 8. This is a fundamental law of the universe. As stuff gets bigger, its volume grows way, way faster than its surface area. And this one little rule explains so much, like why giant elephants need thick, stumpy legs to support their weight, or why a crushed-up sugar cube dissolves way faster than a solid one. Look, a detective can have the most brilliant theory in the world, but without solid evidence, it's just a story. And that evidence has to be rock solid, collected carefully, documented perfectly. It's exactly the same in physics. And that brings us to our last tool, tool number 4, documenting the evidence. This is all about the art and science of measurements. It's about knowing what your numbers actually mean, what they're telling you, and just as importantly, what they're not telling you. The big idea here is something called significant figures. Now, that might sound a little technical, but it's really simple. They're just the digits in your measurement that you're actually sure about, the ones you can trust. They're a way of being honest about how good your measurement tool was. It's like telling another detective, hey, this piece of evidence is pretty solid, or this one's a little fuzzy. Let me give you a quick example. If you measure something and write down 12.3 centimeters, what you're really saying is, I'm totally sure about the 12, and I'm pretty confident about that 0.3. That's 3 significant figures. It automatically tells me that there's a little bit of wiggle room, a little uncertainty in that last number. The really honest way to write it is 12.3 plus or minus about 0.1 centimeters. And that's it. There you have it, 4 incredibly powerful tools. And these aren't just for physics class, not at all. These are ways of thinking that will help you solve problems anywhere, in any part of your life. You are officially equipped. So let's do a quick inventory of your new detective toolkit. You've got the composite sketch for simplifying complex problems. You've got the back of the envelope punch for making smart, fast estimates. You've got the laws of the land to check if your ideas follow the basic rules of the universe. And you've got documenting the evidence to make sure your measurements are honest and precise. All right, detective, it's time for your first case. Are you ready? Here it is. How many grains of rice are in a 1 kilogram bag? Now, don't just pull a number out of thin air. Use the toolkit we just put together. Can you make a composite sketch of a grain of rice? Can you use your back of the envelope skills to make some smart guesses? Give it a shot. See what you come up with. The universe is just full of these little puzzles, just waiting for someone like you to come along and solve them. Go get 'em.